At first, it is just a faint elongated smudge buried in the noise of a survey image. A streak of light drifting across a star field, stacked from a sequence of short exposures as an automated system, tracks a moving point. Astronomers see thousands of these in a season. Most are small asteroids, dormant comets, pieces of ordinary debris. But on this night, a few scientists stop scrolling. Something about this smear is wrong. The rules of comet behavior are simple enough to explain. When an icy body falls toward a star, sunlight and the solar wind push the dust and gas away. Material lifts off the surface, and radiation pressure sweeps it into a tail that, overall, streams roughly in the antisolar direction, away from the sun. The nucleus moves ahead, the tail trails behind, like a flag in a steady wind. Decades of images, from backyard telescopes to space observatories, reinforce this intuition. This object does not obey. In the first deep-stacked CCD frames, its dust tail looks twisted and slightly defiant. Instead of pointing cleanly away from the sun, it bends, curving partway toward the path of motion, as if something is tugging it sideways. The nucleus is there, a compact, star-like core wrapped in a dim coma. But the geometry feels skewed, as though the forces acting on it are being quietly rearranged. The team assumes the problem is earthly. Perhaps it is a processing artifact, a bad flat field, a cosmic ray strike that slipped through the rejection algorithms. They rebuild the stack from raw fits frames, change the reference stars, alter the tracking, rotate and recenter. The tail keeps pointing in the wrong direction. Comparisons begin. Classical comets in similar regions of the sky show the expected anti-solar sweep. Long-period visitors from the outer Oort cloud, plotted under similar illumination, respect the usual geometry. The team pulls archival images of earlier interstellar wanderers and checks their tails as well. None behave like this. None with a main dust feature leaning this far toward the velocity vector at this heliocentric distance under these conditions. More eyes turn to the object. Another survey telescope images it on a different night, under different conditions. The tail is still misaligned. A mid-sized observatory spends hours on long, guided exposures. The stacked image shows the same bend. Amateur astronomers, guided by fresh ephemerides, point cooled CTs from backyards and small domes around the world. Their data, processed with different software and different instincts, reproduce the same quiet violation. By the time you hear of it, the puzzle has already passed through several hands. Somewhere between the pixels and the equations that should describe them, there is a discrepancy measured in a handful of degrees on the sky and a few percent of brightness. In orbital mechanics and in comet physics, small deviations often mean that something important has been left out of the picture. Tonight, we open that picture together. An interstellar object that should behave like so many others, whose tail instead bends the wrong way. If you enjoy this unfolding mystery, subscribe for more Beyond the Solar Veil cosmic documentaries, and follow 3 Atlas along its strange, hyperbolic path. The story begins like many minor body discoveries now do, with an automated alert from a wide-field survey. Atlas, the asteroid terrestrial impact last alert system, adds a new moving source to its nightly list, flagged by software that searches for objects shifting against the fixed stars. At first, it is just a provisional designation and a handful of astrometric points, precise positions on the sky recorded to fractions of an arcsecond. Night by night, that list of coordinates grows. Observatories in other hemispheres pick it up, stitching together a longer arc of motion. The measurements flow to the minor planet center, where orbit-fitting software tries to thread a path through space that matches every data point. For most objects, that path curves into an ellipse, a bound orbit tied to the sun's gravity, with a period measured in years or centuries. This solution refuses to close. The best fit is a hyperbola, a curve that approaches the sun, swings around it once, and then never returns. The eccentricity is not just slightly above 1, it is comfortably beyond, and the inferred inbound speed, corrected to the sun's frame, is too high for a native comet nudged inward from the outer Oort cloud. This body has fallen into our system, from the galaxy beyond the sun's long reach. With that realization comes a different label. The object is designated 3. Atlas, the third recognized interstellar object, following the enigmatic Oumuamua and the more classical-looking TUI Borisov. The 3A marks it as unbound. The Atlas honors the survey that first spotted it. On paper, the new entry looks almost modest. Absolute magnitude, orbital elements, discovery date. But the meaning has shifted. This is not just another member of the solar system's own debris cloud. It is a fragment of another planetary system story, passing through the reach of our instruments. Its trajectory slices into the inner solar system on a path sharply inclined to the ecliptic. If you could hold a scale model of our planetary plane in your hands, a thin disk traced by the orbits of Earth and Mars, 3 Atlas would be like a needle coming in from above, cutting through the disk and out again. Near perihelion, it moves tens of kilometers per second relative to the Sun, crossing the distance between Earth and the Moon in a matter of hours, and traversing an astronomical unit, the Earth-Sun distance, in a matter of weeks. Orbital elements sketch the geometry. The perihelion distance, its closest approach to the Sun, lies beyond Earth's orbit, sparing it the extreme heating that drives spectacular outbursts in some comets. The inclination tells us how much it rises above and below the planetary plane. The longitude of the ascending node and argument of perihelion fix the orientation of its path in three-dimensional space. The hyperbolic excess velocity describes how fast it will be moving once it has escaped the Sun's gravitational influence completely. At any moment, its position can be expressed in astronomical units. 1.40 from the Sun, then 1.2, then back out past 1.5 as it rounds the corner of its closest approach. The intensity of sunlight, it feels, falls and rises as the inverse square of that distance. The density of the solar wind and the interplanetary magnetic field strength change with heliocentric distance as well. The object is not gliding through a static vacuum, but through a structured environment shaped by our star. Knowing its orbit allows astronomers to predict where it will be on the sky weeks and months ahead. They know when it will be best placed against dark, moonless backgrounds, when it will pass nearest to Earth, when it will be near the galactic plane and harder to pick out. They also know from basic physics how its activity should respond to changing distance from the Sun, how much energy reaches any square meter of its surface, how quickly ices should start sublimating, how strong any dust and gas emissions should become. Those expectations feed directly into telescope proposals. Survey snapshots are no longer enough. A global, coordinated campaign begins. Across mountain ranges and deserts, domes open. Pan-STARRS keeps tracking its position, refining the orbit. Larger optical telescopes swing onto target, some using wide-field cameras to capture the full, faint sweep of coma and tail, others zooming in on the inner few thousand kilometers around the nucleus. Time is precious. The object is faint and fast-moving, and chances to catch it at high signal-to-noise are limited. In orbit, space telescopes free from atmospheric blur provide sharp images of the central regions. High-resolution cameras look for jets, narrow plumes of dust, or gas emerging from specific regions on the nucleus. Spectrographs disperse the light into spectra, where characteristic molecular bands reveal which ices are escaping. Spectral features from CN, C2, and other species hint at the underlying chemistry. Infrared instruments measure the thermal glow of dust grains, giving estimates of their temperatures and size distributions. On high, dry plateaus, radio and submillimeter arrays like ALMA tune to lines of carbon monoxide, water, and other simple molecules in the coma. These observations yield gas production rates. How many kilograms of a given species are escaping per second? How quickly the nucleus is losing mass? How much momentum that escaping gas can transfer to the dust and to the nucleus itself? Around the planet, smaller observatories and experienced amateurs fill in the gaps. Their telescopes may be half a meter in diameter or less, but their persistence builds dense time series. They take dozens of exposures per night, stack them carefully, and measure brightness changes that might otherwise slip past. In the weeks between the largest observatories observing runs, these data trace how the coma and tail evolve. Every wavelength adds a piece of the puzzle. Optical images trace the dust-scattered sunlight in the coma and main tail. Infrared data constrain dust temperatures and sizes. Radio and sublimeter spectra reveal which ices are escaping and at what rates, tying composition and mass loss directly to the shapes we see. From that model, you should be able to predict how the tail looks. At any moment, you know where the sun is relative to the object, how strong the radiation pressure is, how strong gravity is, and how fast dust grains of different sizes will be pushed and pulled. You can compute the trajectories of those grains, map them out as they drift away, and then project that three-dimensional structure onto the two-dimensional sky. You can calculate the expected angle between the brightest part of the dust tail and the sun, object line, and how that angle should change as the object moves. For most comets, these predictions work remarkably well. Synchrone diagrams, plotting dust released at different times with different radiation pressure responses, line up with observed tails to within a few degrees. Any remaining discrepancy can usually be blamed on uneven activity, on jets that temporarily bias the release direction, or on small errors in assumed grain properties. For 3i Atlas, those predictions and the images keep disagreeing in the same stubborn way. In frame after frame, the ridge of maximum brightness in the dust tail sits rotated away from the expected antisolar direction, leaning closer to the velocity vector than theory allows even after you vary grain sizes and ejection speeds. The tail's curvature and brightness profile refuse a simple steady-state explanation, hinting that an extra ingredient is missing from the standard picture. Orbit fitting adds another layer. Precise astrometry of the nucleus over weeks and months reveals small but persistent residuals when you assume gravity alone. When non-gravitational terms are added, mathematical components representing a net thrust from asymmetric outgassing, the fit improves. This is not unusual by itself. Many active comets show measurable non-gravitational accelerations. But for 3.8 Atlas, the direction and evolution of this inferred thrust vector do not map cleanly onto the observed tail geometry. The way the nucleus is being pushed and the way the dust is bending seem related, but not in the straightforward way standard models would suggest. Photometric monitoring complicates the picture further. As the object approaches and recedes, its brightness does not follow a smooth, monotonic trend. Instead, the light curve shows intervals of unexpectedly rapid brightening, plateaus, and subtle fades that do not line up perfectly with simple functions of heliocentric distance. Rotational modulation, the changing view of active regions on a spinning nucleus, can explain some structure, but not all. Occasional spikes suggest short-lived outbursts. Gentle undulations hint at more persistent, slowly varying activity. Different teams, working with different telescopes, filters, and reduction pipelines, report different absolute magnitudes. But the relative changes over time agree. They see the same brightening episodes, the same flat spots, the same slow declines. Yet, when they compare these to the times when the tail appears most strongly misaligned, the correlation is imperfect. The tail sometimes bends most dramatically, not when the activity is strongest, but when conditions in the surrounding environment, the solar wind, the viewing geometry, are shifting. By now, instrumental explanations are unlikely. The misalignment appears in data taken with different optics and detectors, at different plate scales, with different seeing conditions. Space-based images free of atmospheric distortion show it. Ground-based images with adaptive optics show it. Stacks of small amateur telescope exposures show it. Independent photometric calibrations and astrometric reductions preserve the effect. The remaining uncertainty lies not in whether the tail is bending the wrong way, but in why. The simplest idea is to complicate the nucleus. If 3i Atlas is venting primarily from a small number of localized areas, cracks, pits, or jets, then the dust leaving the surface will have a strongly preferred direction. If the nucleus is also rotating in a complex way, perhaps tumbling rather than spinning about a single stable axis, the direction of that jet will trace out a pattern in space as time passes. Dust grains released under these conditions will carry the history of that biased ejection, and the resulting tail may tilt and twist in ways that simple, symmetric models fail to capture. You can test this by looking for periodicities in the light curve. A rotating nucleus with large brightness contrast between active and inactive regions will imprint its spin period onto the total brightness. If the same period appears in subtle oscillations of the tail orientation or in the timing of small outbursts, then rotation plus jet models gain support. Early analyses of 3A Atlas hint at possible periodicities, but the data are sparse, and the object is faint. The signal is there perhaps, but not yet clear. Another avenue is to revisit the dust itself. Much of classical comet modeling assumes compact, roughly spherical grains, but aggregates formed in low-gravity environments can be extremely porous, built from smaller subgrains into fragile fractal structures. Such dust has large surface area for its mass and can respond more strongly to radiation pressure and gas drag, so the same radiation field can accelerate it farther and skew the tail's shape without any new physics, simply because the particle's shape reacts differently.
Now.
Composition offers another
Waveform
lever.
stable, but
If the nucleus is rich in
increasing.
highly volatile ices such as carbon monoxide, carbon dioxide, or more exotic species, significant outgassing could begin, while the object is still far from the sun, at heliocentric distances where water ice would remain mostly inert. Dust released under those early cold conditions might follow trajectories quite different from dust released later near perihelion. By the time we observe the tail, it could be a superposition of grains emitted under a wide range of distances and solar wind conditions, layered in space, in a way that standard near-sun activity profiles do not represent. It is also possible that the interactions with the solar wind and the interplanetary magnetic field are more complex along this particular trajectory than usual. The ion tail, tied directly to those fields, may be bending and keying in response to variations in the heliospheric environment. Dust grains, though electrically neutral, move through the same space. Local structures in the solar wind, shocks, shear flows, turbulence, could subtly reshape the dust distribution over time. Coupling these detailed plasma effects into dust models is difficult, but not impossible, if solar wind measurements along related radial directions are available from spacecraft. At the speculative edge sit ideas that brush against the notion of design without resting on it. Swarms of debris from a fragmented body could be arranged into streams whose density and geometry mimic some aspects of controlled propulsion. Large, thin shards might react to radiation pressure like